Okay, so yeah, get equipped for IIT JEE main, and this is ionic equilibrium. So previously we did chemical equilibrium, now it's gonna be ionic equilibrium. So it's like it's also chemical equilibrium, just with more approximations and more terminology. And yeah, let's go. Question number one. For pure water, pH increases and pH decreases with rise in temperature. When you have increase in temperature, your uh, both concentration of OH minus and concentration of H plus both increase, and that means pH and POH, which is like just negative log base 10 of the concentration. So anytime you see P in front of anything, just put negative log base 10 instead of P. So negative log base 10 H. When you have pKa, put negative log base 10 Ka, and so on. So pH and POH, they decrease with rise in temperature, right? Because negative log base 10. Log base 10 increases, negative of that decreases. So it's gonna be D. Right. Uh, 0.1 millimole of something present in 10 milliliter acid solution of 0.08 normal HCl. But 10 milliliter, right? And 0.1 millimole of this thing. Okay. In 10 milliliter acid solution of something normality HCl. Now H2S is passed to precipitate the CD2 plus ions. Okay, cool. So H2S will give H plus, and that's why this will happen, right? I think, right? CD2 plus ions, and the other SO4 2 minus ions. What will happen? Well, they are just there. They aren't doing anything. Um. Okay. Okay. Fine. Precipitate all of the ions. Okay, the pH of the solution after filtering off the precipitate, boiling off H2S, and making the solution 100 milliliter by adding H2O approximately. So I think what they mean is that it will precipitate all of the CD2 plus, right? So if it precipitates everything, then it's still 0.1 millimole. You just have the normality, you don't know anything else. Okay, how am I supposed to? The pH of the solution after filtering off the precipitate. Okay, boiling off H2S, and making the solution 100 milliliter by H2. So you remove the precipitated CdSO4, sorry, Cl, right? I think it's CdCl2. You remove that. There's still SO4 2 minus roaming. We have some H plus over there. The pH of the solution after filtering of precipitated, boiling of H2S, so there's no H2S anymore. Making the solution 100 milliliter by adding H2O is approximately. So, okay, this is weird. You know, there's a CdSO4, there's HCl. How does this precipitate though? CD. Okay, think about it. Maybe it's like CD sulfide, cadmium sulfide. Does that precipitate? Maybe. Could it be CdCl2? Okay. Right. So I think we have to assume that H2S is like a strong acid. Is it? But you boil that off anyway. Right. So you just add H2S and then remove it. So actually it doesn't play any role. Oh, then it's just HCl. So you actually precipitated CdCl2 ions over there. No, wait, you add H2S till you precipitate all of. I think it's like CdS is what's precipitating. And you have 0.1 millimole of CdSO4. So you will need 0.1 millimole of H2S. Alright, that means 0.2 millimoles of H plus. And that in 10 milliliter. So 0.2 millimole upon milliliter, right? So 10 milliliter. And that's gonna be 0.02 normal. That's added. So that plus 0.08, that will be 0.1 normal H plus, right? Or molar H plus, because it doesn't make a difference. The pH of the solution after filter precipitate, boiling of H2S and making the solution 100 milliliter. So you increase from 10 to 100 now. So your molarity decreased by 10, so 0.01. polar H plus. So now the pH is approximately, and this is like 10 power negative 2. So negative log base 10 of 10 power negative 2, that's going to be 2. So pH is approximately 2, I think, because, yeah, and it should be 2. Don't consider the water ionization in there. It's negligible. Question number 3. Okay, zinc salt is mixed with something of molarity 0.021. The amount of Zn2 plus remains unprecipitated in 12 milliliter of this solution would be. So this guy has molarity 0.021. Okay, zinc salt is mixed with this. Amount of Zn2 plus that remains unprecipitated. So let's assume that that salt was a good electrolyte and it just gave Zn2 plus. KSP of ZnS. Oh, so okay, so S2 minus plus Zn2 plus that precipitates. Huh. So, and then what about NH4 plus? Doesn't that do anything? Okay, we don't actually even care about it. So yeah, remains unprecipitated in 12 liter of the solution would be. So this thing is molarity 0.021. How much of zinc was added though? I don't get it. How much of zinc? Maybe it was just a little bit of zinc. I don't know. How am I supposed to solve this? Amount of seconds 2 plus that remains unprecipitated in 12 milliliter of this solution. Hey, look, you are not giving us how much of Zn2 plus was there initially. How am I supposed to do this thing? Mixed with this solution of molarity something. Okay, zinc salt. You don't give how much, so we'll just say it's a very less quantity, maybe. Yeah, right. And how am I supposed to do this otherwise? If it's a very less quantity, then it will like completely like it will completely dissociate, and then your Zn2 plus will combine with that to give that. Okay, cool. So your S didn't actually change. It's just that ZnS came down. Oh wait, okay, I get it. I get it. So you keep on adding the salt till it starts to precipitate. Okay, I understand. Fine. So yeah, like if you add just a little bit of salt, it will precipitate. It won't precipitate, right? And if you keep on adding the salt, then after a point, your KSP for this guy will be equal to, sorry, your QSP will be equal to KSP, and then it will precipitate. Fine. So you need to find what that concentration is, because that concentration will remain constant. All right. So you want the amount. So it's like in, let's just find the molarity. So molarity times so this guy S2 minus is in molarity 0.021. That's equal to KSP. So this guy will be 4.51 into 10 power. So this is like I should say 2.1, two jumps into 22. This times 2 is okay now. So like 2 point. So we got 31 over there. That is approximately, yeah, it's like 2.1, close enough. If you want 2.15 maybe. So 2.15, that is the molarity. And you don't want the molarity, you want the amount of Zn2 plus in grams. And this is in what volume? 12 milliliter of the solution. So 12 times this thing. 12 times, hey, if that's 12, why don't we do it directly? So 4 point, oh, this is into 10 power negative 2, 22, okay. So 4.51 times all of that upon 2.1, and look at that, that's gonna be 4, 0.7. Okay, so 4 into 45.1 upon 7, 4, 4231. No, doesn't work. 451. That's a bad kind of number. Where what was question? No, question number three, right? Uh, 4.51. Yeah, that's the thing. Then only 22. It's about 40. You want 55, 54. It's close enough to 56. It's like 0.8 maybe. Right, approximately that. This much is your moles, and now moles upon the mass. So zinc has what mass? We don't know. Okay, but it's uh, zinc. We don't know. Iron is 26. Cobalt, nickel, copper, zinc. Right. So 27, 28, 29, 30. It's gonna take it as 60, even though it might be more than 60. Right. So now it will be what? 25.8 upon 6 into 10 power negative 23, 25.8, it's 24 and 18. Oh, that's nice. This is going to be equal to 4.3. So 4.3 to 10 power negative 23. Is that anywhere? It's not, of course, because why would they want us to do anything? Ah, come on. Why is that not there? Look, that's 0.021. Yeah, that's correct. Mm. How am I supposed to solve this now? It's 10 power negative 23, about that order. So look at the options. I think C might be the way to go, right? Maybe, you know, 2 plus. Mm. So I'm gonna go with C. Next question. Question number 4. Okay, to prepare a buffer of pH, something amount of this to be added to 500 milliliter of 0.01 molar NH4OH solution. Buffer of pH 8.26. Okay, amount of something to be added to 500 milliliter, the 0.5 liter of 0.01. So that's gonna be 5 10 power negative 3 moles of NH4OH. Okay, wait, no need to for doing that. I just put the concentration directly. NH4OH solution. Okay, cool. So just basically it's just NH3. Uh, yeah. So NH4 plus has pKa 9.26. That plus OH minus. That's gonna give us NH4OH, right? And NH4. Oh, okay, yeah. NH4OH. I mean it dissociates as NH4 plus and OH minus, right? So just already prepare a buffer of this thing. Of pH is given. Okay, cool. So amount of that to be added, 500 milliliter of this. Okay, what do you know? You know the concentration of NH4OH, or in fact, let's say NH3. You know, that's better to understand. NH3 times concentration of H plus upon concentration of NH4 plus, right? This thing is our pKa. This thing is our Ka, right? And once you know what this quantity is, we are basically done. And what you know what this quantity is, right? Oh, so then you can figure out what this is. And actually, you already know what this is, so it's just that, right? So what is this? NH3. So 0.01 molar, right? is 10^-82, and H plus it's 10 power negative 8.26 upon, we don't know what this is. Okay, so it's gonna be like 2x upon what, how much liters? 500 liters by 0.5, right? That x is like how many moles of NH4 to SO4 you add. This is supposed to be equal to Ka. Ka is so pK is given, that means like 10 power negative 9.26. Okay, so yeah, there we go. 10 power negative 1 equal to 4x. Oh, that was not that bad. So x is just 0.1 upon 4, which is 0.025. These many moles. Okay, so that's gonna be B. Question number 5. What is the percentage hydrolysis of NaCN in N by 80 solution when the dissociation constant for HCN is this thing and Kw is this thing? Okay, dissociation constant is given, Kw is given, and we want the percentage hydrolysis of NaCN. So yeah, so once you know what this is, you can figure out the reverse dissociation constant. So basically Kd thing for NaCN, and that would just be this guy. So 10 power negative 40, that's our Kw upon this, right? So just do it by yourself, see if it works or not, and you'll see, yeah, that's the way it is. So that's gonna be 10 power negative 5 on 1.3. Ooh, that's a bad value. Okay, and you want the percentage hydrolysis of NaCN. So Na is not gonna hydrolyze, it's just Cn minus that is gonna hydrolyze, and for that the constant is this guy. So yeah, so it's gonna be concentration of HCN, concentration of OH minus upon concentration of Cn minus, right? And what is the initial? Okay, it's N upon 80. So N upon 80 into alpha squared upon 1 minus alpha squared. Not squared, just 1 minus alpha. N upon what? N upon 80. So 1 upon 80, in fact. Yeah, right? Normality. So it works like that. Cool. Yes, and that is 10 power negative 5 upon 1.3. Oh, so some alpha squared upon 1 minus alpha is equal to 80 upon 1.3 into all of that stuff. So 8. Okay. 80 to 10 power negative 3 upon 13. So you know that, like, what is this value gonna be? Come on, okay, you let's try it like that. So 80 upon 13, that is, think about it, 78 would be 30 times 6, which, yeah, so approximately 6 10 power. But then you want to get square root of that and whatnot. Okay, that's 4 times 20. 20 will also be like, so 16 times 5. 5 upon 13. Not a good idea. What is 5 upon 13? 0.50 for that. You just need 39, and then you will have 51. Okay, that is 4. So, oh, that's approximately 4. Well, that's nice, because then you can write the 16 times 4 over there, right? So this is approximately 16 times 4. And that means alpha is, if you ignore this thing, that will be approximately 4 into 2, which is 8 into 10 power negative 2. And yes, then it's ignorable because this is actually 0.08. It's small enough. So yeah, that's alpha approximately. And what do you want? You want the dissociation constant for, okay, yeah, you want the percentage hydrolysis. So this in percentage, about 8%. So C, I think. Question number 6. Question number 6 is the concentration of fluoro, okay, whatever acid, which is required to get H plus fluoroacetic acid. So it's acetic acid, 63OH, but with a fluorine attached to it. Okay, cool. So it's like this guy. So it's monobasic, that's all we need to know. So Ka of this acid is given, which is required to get concentration of H plus that much. Okay, so it's like C into alpha squared upon 1 minus alpha. You know the thing, right? It's C00 initially. We got Ha. This is H plus A minus. Then this becomes C into 1 minus alpha. Then becomes alpha, C alpha and C alpha over there. And then you can find the reaction quotient like that. And this should be equal to your Ka, which is 2.6 into 10 power negative 3. And you know what the H plus concentration is, then you know what C alpha is basically. Your C alpha is oh, that's, yeah, that's big enough, so we can definitely do it. 1.5 to 10 power negative 3. There we go. So you know that that's the case. Cool. Right. Okay, so once you know C alpha, just put that over there. So like 1.5, which will divide both the equations. That will give us alpha upon 1 minus alpha is 26 upon 15. So 15 alpha equal to 26 minus 26 alpha. So alpha is 26 upon 41. There we go. That is our degree of dissociation. And what do you want? The concentration. Okay, it's required to get this much, right? So once you know what alpha is, just divide by that. C will be 41 upon 26 into 1.5 into 10 power negative 3. That is it. That's the concentration. Now we need to get it done. So it's like 3 upon 2. That will be 123 upon 52. So this is this times 2 is gonna not do it. It's like bigger than 2, I think. Yeah, bigger than 2 into 10 power negative 3, of course. So bigger than that. Where is it? Oh, come on. Yeah, there it is. So B, 6B. Next question. Question number 7. Okay, the number of H plus ions present in 10 milliliter of a solution of pH equal to 3R. H plus ions present in 10 milliliter of solution of pH is given. Okay, cool. You just gave us the pH directly. Come on, so it's 10 power negative 3, that's the concentration, and that times 10 milliliter. 10 milliliter is just 10 power negative 2 liters. So 10 power negative 2 times 10 power negative 3, that's the number of moles, which is 10 power negative 5. And that times Avogadro's number, right? So 10 power negative 5 times 6.02. Yes, 10 power 23 minus 5, that's 10 power 18. So there we go. Where is 18 over there? It should be B, I think. So yeah, right? 10 power negative 3 and 10 power negative 2. Yes, it works. A solution contains this much each of NaCl and NO2 CrO4 solid AgNO3. What time is it? Did I go for 1 hour? Okay, it's just half an hour. Oh no. Number of H plus ions present in 10 milliliter of a solution of pH equal to 3R. Hey, that we did. Solution contains something each of NaCl and Na2 CrO4. Solid AgNO3 is gradually added to it. AgNO3. Okay, which of the following fact is true? So AgCl precipitates. Okay, and NaCl, Na, just remove that. CrO4 2 minus. Oh, so Ag2CrO4 also precipitates. Oh, that's nice. And solid AgNO3 is added to it. What about AgNO3? So does that precipitate? I don't think that does. So anyway, you just have a lot of Ag plus around there. Yeah. And it contains equal concentration of both of these. Okay, cool. Right. So divide by that concentration, you will have those comparisons. And then the concentration of Ag over here and concentration of Ag2, sorry, concentration of Ag squared over there. So for the first guy, the concentration is just 1.7 to 10 power negative. What is this? 10 power negative 10 upon 0.05. Right. That's the concentration of Ag that you need. For the second guy though, it is 1.9 into 10 power negative 12 upon 0.05, and that guy is square root. Okay. So this will be like 5 into 10 power negative 2, so it's going to be 10 power. Yeah, this is going to be 8. Something like that. So as you can see, 10 power negative 10, the square root of that is like 10 power negative 5, and this guy is just 1.9 upon 5. Square root of that's like 0.2. The square root of that is going to be bigger than 0.2, of course. What is this? Like it's actually close to 2, so 0.4. Yeah, square root of that, bigger than 0.4. And that times 10 power negative 10, but this guy has 10 power negative 18, it's smaller than that. So this will precipitate first, I mean the one with that, which is AgCl. So AgCl precipitates first, and then this thing precipitates. Okay. Yeah, so A. Question number 8. The second ion starts precipitating when half of the first ion is precipitated. But it's a solid AgNO3. What about it? We don't know anything about the concentration, right? Whatever. Oh, okay. So you mean like when the concentration is such that it starts to precipitate, and at that point, uh, half of it is down, but no, but then it's not an equilibrium anymore. That doesn't make sense actually. So no, this thing AgCl will precipitate completely without giving any chance for this guy to precipitate. So D is not correct. Ninth, approximate pH of 0.01 molar 10 power negative 2 aqueous H2S solution. So K1, K2 are given. Look, K1 is much bigger than that. Okay. Right. So let's just ignore K2 for a while and let's see what happens for K1. Right. So 0.01, that's 10 power negative 2 times alpha squared upon minus alpha. That thing is K1 is 10 power negative 7, right? 10 power negative 5. Is that H2S, right? I guess H is minus plus H plus. 10.87, that's kind of bad value. Okay, whatever, but that's the thing. So 10.85 is actually, so alpha will be less than 10 power negative 2.5, which is less than 0.01. So it's actually approximately equal to this thing. Right, so look at this. The total concentration will be 10 power negative 4.5 for HS minus, and H plus concentration is also 10 power negative 4.5. And then if you consider the second dissociation, right? Second dissociation has this as the constant. So like concentration of H plus is already very big, right? Because 10 power negative 4.5, yeah, so it's much bigger than this thing. It's like very tiny, 10 power negative 13. And the denominator, it's like less than the concentration of HS minus, right? The one that we found. That means the concentration of S2 minus will actually have to be very small. Yeah, it will have to be very small. And that means there's actually not much dissociation for the second one. So most of the H pluses come from the first dissociation. And yeah, so 10 power negative 4.5, that's the concentration of H plus. So our pH would approximately be 4.5. So 9A. Question number 10. Question number 10 is the self-ionization constant for pure formic acid. Something has been estimated as 10 power negative 6 at room temperature. Self-ionization constant. Okay, fine. The density of the formic acid is something percentage formic acid molecules in pure. Okay, so K is 10 power negative 6. Density is given. Density of formic acid is 1.22 gram per centimeter cube. The percentage of formic acid molecules in pure formic acid that are converted to formate ion would be approximately fine. So the percentage of molecules. So you need to deal with mole fractions. You want to go from mole fractions to, well, first of all, of course, this and this both will have X, and this guy's mole fraction will, sorry, the mole fraction of the actual liquid will be approximately 1. Okay, and then from mole fractions we're gonna go to concentrations, right? So how would we do that? Just like N of some species upon N total, right? So basically it's like, yeah, the other species just has like whatever N it is. It's just Just, yeah, it's just the pure liquid itself. So okay, and wanna get the concentration, so this is already there. We just need to multiply this by something to convert it to volume. So this times the molar mass, that will give us the weight of the whole solution, and that upon the density, that will give us the volume, right? So we need to multiply the denominator by m upon rho. That means we need to multiply this whole thing by rho upon m. So density upon the molar mass. Right, we already know what the density is, 1.2 gram per centimeter cube, but convert that first. So a gram is 10 power negative 3. Okay, wait. Should we convert this first? No, 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 no. Don't do it. Okay, so it's like, but yeah, centimeter cube, convert centimeter cube to liter. Don't convert gram to anything. So like 10 power negative 3. So 1.22 10 power negative, no, 10 power 3, because we said decimeter. Right. So yeah, 10 power negative 3 in the bottom, on the top, 10 power positive 3 upon upon m, and m is what's m? What was I doing once again? Your molecular mass for what? Formic acid. So HCOH. So H2 O2 carbon. And that times the mole fraction. Right. That's the concentration. Yeah. Um, so this concentration squared. Oh, come on, seriously. This concentration squared, that is where did it go? Come on, question number 10 is k. K is 10 power negative 6. Cool. So remove this, it's in power negative 3. So x will be, so what's this? 2 plus 32 is 34. 34 plus 12 is 46. Right? Yeah. 1.22 to 10 power 3 into 10 power negative 3. 10.86. This is going to be 46 upon 1.22. Come on. How does that make sense? Like, no, it's 23 and 46. It could be anywhere between that. You can write at 4.6 upon 1.22 to 10 power negative 5, I think. Right. So that's your mole fraction, I think. Okay, so the percentage of formic acid molecules in pure formic acid that are converted to formate ion. So just this much, right? Would be approximately. So this much, yeah. And this times 100, so it's going to be 10.3. This much percentage. It's like 4, yeah. 4 times this, that would be 4.88, which is okay. So it's like something slightly less than 4. 10 power negative 3. So yeah, so B should be correct. There we go. Question number 10 is B. Question number 11. Okay, the resultant pH of a solution when 200 milliliter of an aqueous solution of HCl is mixed with 300 milliliter of an aqueous solution of NaOH. pH of a solution. Okay, so pH is this thing 10 power negative 2. That's the concentration, 0.2 liter, like 0.2 into 10 power negative 2. That's the concentration of H plus, moles of H plus 300 milliliters, so 0.3 times 10 power of NaOH. Okay. So pH 12. Well, that's weird. So what's POH? POH will be 2, so 10 power 82, but now it will be minus. So this minus that plus, and this will be basic, right? It's going to be basic. And that upon 0.5, because now they're combined. Right, so this is going to be 0.1, or just like 1 upon 5 10 power negative 2. This is the concentration of OH minus. Right. And this is like what? 0.2, so 2 into 10 power negative 3. So what is our POH? Our POH is 2 minus log base 2 of log base 10 of 2, which is like approximately 0.3. That's our POH. Our pH will be 11 plus 0.3, which is 11.3. So that should be the answer, which is B. Question number 12. Question number 12 is ionization constant of NH4 plus in water is 5. Just wait a second. Yeah, sorry. So, question number 12. The ionization constant of NH4 plus in water is 5.6 into 10 power 10 at 25 degrees Celsius. The rate constant for the reaction of NH4 plus and OH minus to form NH3 NH2O. Right, so have concentration of NH3. This guy is 3.4 to 10 power 10. Okay, and then it's constant for NH4 in water, right? So you know that. Cool. Haha. Fine. The rate constant for proton transfer from water to, oh come on. So what we're saying is like concentration of H plus, concentration of NH3 upon concentration of NH4 plus, right? That guy is 5.6 into 10 power negative 10, and that is that. Okay, the rate constant for proton transfer from water to H2, sorry, from water to NH3. So for this reaction, right, H3O plus NH3 gives H2O plus NH4 plus, right? So this reaction over here, it only has H plus. So if we reverse this reaction, 5.6 to 10 power negative 10, and then we add this reaction. Sorry, I think it should be like H3O plus. Wait a second. H3O plus is the same thing as H plus. So yeah, like what is this? How is this supposed to make sense? Right. I mean, even if you like remove that H2O, it doesn't actually make any difference, right? So that is in fact the equilibrium constant for this reaction, right? What's the big deal about it? I don't understand this. For proton transfer from water to NH3, so NH4 dissociation, you have that. Do you have something for? Oh, you also have this guy. Okay. Wait, but then H2O, a proton transfer from that. Proton transfer from water to NH3. So are we talking about neutral molecules like H2O and this becomes OH minus then? Is that what we're saying? But we already have the reaction constant for this. It's going to be 1 upon this guy, right? Yeah, like I don't know what you mean by that. Proton transfer from water. By that, I assume you are talking about neutral water molecules. To NH3 is okay. I'll just say it's like 1 upon this guy. So 10 power negative 10, right? About that. And 1 upon 3.4. Okay, it should be like even less than that. So it's definitely not this. It's not that. It's not that. Oh, wait. Why is this so small? Oh, yeah, it should be small because it's dissociation. So, yes. And this is also small. Fine. Okay, I don't understand what they're asking. So I'm gonna go for intuition and say it's like D. Yeah, it looks correct. Because I mean I know it's not correct because 1 upon 3.4 is less than 1 and 6.07 is not. I just don't know what they did over here. What exactly do they want us to find? Whatever. Next question. Question number 13. So 13 is 1 liter of water contains 10 power negative 7 mole of H plus ions. Degree of ionization greater of water is approximately. Okay, 1 liter of water contains this much moles of H plus ion. Okay, so degree of ionization of water is, oh, okay, I get it. Degree of ionization. Fine. So your concentration of water fuel, what's that? So the density, that's just 1 gram per centimeter cube. But 1 gram is basically 1 upon 18 moles. So 1 upon 18 mole per centimeter cube, and 1 centimeter cube is nothing but 10 power negative 3 liters. So it's 1 upon 18 to 10 power negative 3 molar. That's the concentration of water, and that times alpha. So alpha upon 18 to 10 power negative 3, that thing is 10 power negative 7. That's what you're saying. So alpha will be 18 to 10 power negative 10. So there we go. Oh, come on. Oh yeah, 1.8 to 10 negative 9. That also works. So 13b. Question number 14. Okay, the pH of 0.1 molar solution of the following salts increase in the order. Okay. uh, 0.1 molar solution. Okay, fine. Increase in the order, that means it should get more and more basic. So NaCl is like neutral, pH is approximately 7. NH4Cl, that's acidic. So it should be lower, not upper. So this is not correct. HCl, of course, that's not even a salt though. I don't know why they put it there. Okay, then NH4Cl, then NaCl, then NaCN. Yes. So B is correct. 14B. Question number 15. Come on. Number 15. Okay, the number of S2 minus ions present at 1 liter of 0.1 molar H2S solution having concentration of H plus equal to 0.1 molar is S2 minus ions present in 1 liter of 0.1 molar H2S. Okay, so here is the concentration. Okay, concentration of H plus is 0.1. So the same kind of question as before, and this is just very less than that. H plus concentration is once again very big. Well, first of all, ignore K2 and find what concentration is of HS minus. Right. Maybe it will dissociate very, very small, in very small amounts. That means your H2S is 0.1 most of the time. Yeah, so H plus and H2S concentration is the same, and that means concentration of HS minus, that will be this thing, 10 power negative 7 mole. Oh, that's it. That's all we need to know. So everything works out. And the number of S2 minus ions present. So if it's 10 power negative 7 mole molar, that's the concentration of HS minus ions. Then a little bit of dissociation of that. This will be 1.1. Oh wait, what was I doing once again? So it's like 1 point, okay, 10 power negative 7, that's this quantity, and then you have 0.1. That times concentration that we don't know, so C, and that is equal to 1.1 into 10 power negative 13. So C is, so it's like 10 power negative 6 over there. C is 1.1 into 10 power negative 19. Right, that's the concentration. That's not what we want. We want the number of S2 minus ions. So 1 liter of that. Okay, cool, got it. These many moles also, and that times 6 point all of that. So yeah, into 10 power 23, so it's gonna be 10 power 4, right? That times 6 point all of that. So yeah, it's gonna be B, I think. 15B. 16th. Okay, a certain buffer solution is obtained by mixing equal moles of X minus and HX. The Kb for X minus is 10 power 10. The pH of the buffer is equal moles of X minus and HX. Okay, the KB for X minus is this much. KB for this guy is that much. Okay, okay, that's weird. So what do you know? Concentration of OH minus, concentration of HX, which already we know is okay, whatever. So HX upon concentration of X minus, concentration of O, concentration of H2O. Well, ignore that. Just ignore that. Don't take that into account. The KB is 10 power negative 10. The pH of the buffer is right. So the pH of the buffer is fine. As you can see, this thing is just 1. Ignore that. So OH minus concentration is 10 power negative 10. Yeah. Right. Right. If you try to change this thing, like mixing equal moles of, yeah, so that would have this 10 power negative 10 concentration. But that means like, oh, come on. Okay, H plus, we know it's 4, but does this work out? So concentration of H plus is 4, concentration of OH minus is, but if you want concentration of H plus equal to 4, like for that to happen, you must leak some H plus into it. And how does that actually work? Equal moles. So okay, if you have like really large quantities of X minus and X, this works actually, and that's what a buffer is, right? So it will have a, it won't change these concentrations. Yeah, so the pH of the buffer, that will be 4. This should be 10 power negative 4, but yeah, that's 4. So A. And question number 17. Question 17 is the self-annihilation constant of NH3 is given by this thing is 10 power negative 30. How many NH2 ions are present per centimeter cube? Okay, the same thing as that. Per centimeter cube of pure liquid NH3. Okay, cool. So you know that concentration of NH2 minus, that will be 10 power negative 15, right? What's the density though for NH3? Oh, you don't actually need that, right? So you just want how many ions per centimeter cube. So 10 power negative 15 mole per liter, and a liter is basically 1000 centimeter cube, and that times what, 1 centimeter cube. Wait, question number what? Question number 17, right? Per centimeter cube. Yeah. So it's just that it's gonna be 10 power negative 18 moles. There we go. Ion. Okay, how many ions that means in particles? So this times, oh my god, this number. So 16 to 10 power 5, which is B. Which number 18. Okay, the precipitate of M2S3 just begins to appear on mixing equal volumes of solution X having concentration of M3 plus equal to this thing, and Y having concentration of S2 minus equal to this thing. The value of KSP maybe just appear on mixing equal volumes of solution having concentration of M3 plus as this, and Y having concentration of S2 minus this. Okay. And it just begins to appear. Fine. Equal volumes. So the final concentration of M3 plus, that will be 2 into 10 power negative 4, and of Y it will be 10 power negative 3. And yeah, like the value of KSP maybe. So M2S3, so just need this concentration squared times this concentration cube. That is our KSP basically. Isn't that correct? So yeah, the value of KSP, that will be 4 into 10 power negative 8 and negative 9. State 17. So 4 into 10 power negative 17, that thing is A. Oh, it should be now. Question number 19. Okay, and acid indicator HIL has Ka equal to this thing. The acid form is red and the basic form is blue, which of the following is correct? Okay, so acid indicator HIN. This gives H plus and ion minus, right? So the acid form is red and the basic form is blue, right? Okay, so let's find when we have um, oh, it has dissociation constant is given. Okay, fine. How does that even make sense? Because all you give is just that. You don't give when it starts to show, right? You don't give like when it becomes reddish and bluish and whatnot. Okay, which of the following is correct? pH equal to 5 when indicator is 75%. Okay, so like that. You wanna find like that? Okay. Okay, fine. So the thing for indicator is that it will be in very small amount and concentration of H plus will be in very large amounts. So yeah, essentially concentration of ion minus upon concentration of HIN, that will be our K value, which is 385 upon concentration of H plus, which is 10 power negative pH, right? And yeah, so an indicator, right? So when pH is 5, when pH is 5, this will be 10 power negative 5, so this will be equal to 3. So it is 75% ion minus. Ion minus is blue, so it's 75% blue. And when it is 25% red, that's when, yeah, pH equal to 5. So C should be correct. And what about 4.05? So when pH is 4.05, so 4 and then that times 10 power negative 0.5. I'm not so sure what 0.5. Come on, how that would make sense? 4.05. Okay. Yeah, whatever. So I'm gonna ignore this thing. Right, this says 10 power negative 4. Yeah. So this will be 3 to 10 power negative 1. So that's like 0.3. Approximately 1 by 3, you know. So cool. Approximately 1 by 3. And that means, oh no. No, don't do it. Fine. Is this good? Is this okay? It's approximately 1 upon 3. Previously, what was it? It was just 3. Okay, fine. And that means at this, what actually happens is, okay, so B is wrong. It's just wrong. What's D? Indicator is 75% blue, so iron minus is 75%. No, no, it's 75% red. That would have been correct. And that means C is the correct option. Okay, let's go to question number 20. Question number 20 is 0.1 mole of NaOH is added to 1 liter of solution containing 0.5 mole of ammonium chloride. The pH of the solution will be 1 liter of solution containing 0.5 mole of ammonium chloride. Okay, the pH of the, okay, so Kb of ammonia is not of ammonium chloride. So that's just 0.1 mole and that's 0.5 moles and plus 0.1 mole of NaCl, no, NaOH, right? And this can be also, I mean, doesn't matter what reactants to start with as long as it's the same material. So this can also be written as 0. Right? Equilibrium will be attained anyway. We can write this as 0.4 NH, 4 plus Cl minus, and 0.1 NaCl, like that, right? And also 0.1 NH3 directly. Yeah, because, right, or I should say NH4OH, but then of course it's just NH3. Yeah, and then not think about this Cl minus, right? So Kb for NH4OH is 1.8 into 10 power negative 5. That means concentration of NH4 plus OH minus upon concentration of what? NH3 basically. That thing is 1.8 into 10 power negative 15. Sorry, into 10 power negative 5. And right now you have this and that. So yeah, and is there anything else in this solution? Not really. There's no NaOH or anything. The pH of the solution will be, I think it's a buffer, right? Right, because this is actually an inert, it's not doing anything. Milliliter of solution containing, right? So these are moles, but okay, so NH4 plus, it could be like 4 upon 1, then 4 concentration of OH minus, it could be that. So concentration of OH minus in that case would be 1.8 upon 4 into 10 power 5. I mean, it can kind of work, no big deal. And if it's that much, it's that big, right? Then 10 power negative 14 upon that. Yeah, that seems actually doable. So 0 point something. So 0.4 and then 20. So 0.45, right? 16 bit, yes. That's like 4.5 to 10 power. It's 10 power negative 5 or 10 power negative 6. That's what the concentration of OH minus would be if this has to happen. Now, concentration of OH minus is like generally 10 power negative 7. And if you want this to happen, then some of NH3 some of NH3 must produce that OH minus, and you just need this much of concentration. And actually, the NH3 is just 0.1 molar, and that means there's not much change in concentration of NH3. So it works. It's like a buffer solution, right? So you got OH minus, and what do you want? You want the pH. So that will be 10 power negative 14 upon all of that stuff. 10 power negative, let's see, what's this, negative 6 over here. So 8 4.5, that is the concentration of H plus, like 8 plus log base 10 of 4.5, right? This thing, it will be what we want. Yeah. So it's definitely bigger than 8. I think it's this value, because like log base 10 of 4, that would be 0.6, and then 4.5 is not much different, so it's 8.65. Yeah, I'm gonna go with D. Question number 21. Okay, the pKa of acetylsalicylic acid, aspirin. Oh, okay, yeah, of course. Is 3.5. The pH of the gastric. So is aspirin monobasic or what? What is aspirin? Aspirin was this guy, right? Like you had this phenol acylated, right? You had acylated phenol, and this was having an acid group, right? So it's actually a monobasic acid. That's all we need to know, right? So monobasic acid, aspirin is 3.5 pKa. The pH of the gastric juice in human stomach is about 2-3. Okay, and the pH in the small intestine is about 8. Aspirin will. Oh, so in different pHs, what happens to aspirin? So it's like low amounts of aspirin will be inserted in this. That's what is gonna happen, I think. So it's basically HA kind of. So HA is H plus plus A minus, and your K for this thing is, so pKa is 3.5. So 10 power negative 3.5 equal to concentration of H plus concentration of A minus upon concentration of HA. So there we go, divided by that. So it's like 10 power negative pH. So 10 power pH minus 3.5. Yeah, there we go. So right now in stomach, where is it? Question number 21, right? In stomach, the pH is about 2 to 3. So this thing is like 10 power negative 1 maybe. Okay, so 2 to 3, that could be 0.5 or negative 0.5. Okay. Hmm. Both of these are actually very close to 1, right? 10 power 0.5, that's like 3 point something, and for negative 0.5, that's the other way around. It's like 1 upon 3 point something. Okay, and in intestine, it's 8. So 8 minus 3.5, that is 10 power zero point 0.5, and then 7 minus 3 is 4. So 10 power 4.5, and that's a big value. That means its concentration of A minus is much bigger than concentration of HA. So it will be ionized in small intestine. So almost completely. Okay, ionized in stomach and almost unionized. Wait, what? Ionized in small intestine and almost unionized? Not really, because not completely ionized in both of them. Okay, almost. Okay, fine. So I'll have to go with D, even though fine. So 21D, right? I mean, it shouldn't make sense. It's just 2 to 3, and I don't know, man. Okay, whatever. Question number 22. Okay, cool. Ka for HCl is this thing. For maintaining a constant pH, the volume of 5 molar KCN solution. What? Okay, for HCN, Ka is this 5 to 10 power negative 10. Fine. For maintaining a constant pH equal to 9, the volume of 5 molar KCN solution required to be added to a 10 molar, okay, to a 10 milliliter of 2 molar HCN solution is, right? So 20 millimoles of HCN, 20 millimoles of HCN, right? Concentration of H plus is, oh, so pH is 9. Okay, what? It's basic? What? So, yeah, it is. Okay, fine, 10.89. So for maintaining a constant pH equal to 9, it's okay, no big deal. Okay, and what? Like, how many moles do you need? What's our pKa? Ka is this thing, 5 into 10 power negative 10. That's gonna be 10 power negative 1, so it's like 0.5. That means N is 10 millimoles. Right, so you need 10 millimoles, and yeah, well, what's the molarity? 5 molar, right? So you need 2 milliliter of this much solution, right? You don't need anti-log of all of that. And why would you need this? I don't know. Yeah, why would anybody need that? It's just pH equal to 9, so integer, good. So C, 22C. 23. The minimum moles of NH3 required to be added to 1 liter of solution, so as to dissolve 0.1 mole of AgCl by the reaction. 1 liter solution. Okay, so 1 liter solution, just 1 liter solution, nothing else good. So as to dissolve 0.1 mole of AgCl. And NH3 is there. Fine. Alright. By this reaction. So NH3 is also having some kind of activity over there. Okay. And minimum moles of NH3. It's like 0.1 moles of AgCl. And that means this is 0.1, this is 0.1. K formation for this guy is given. Okay, that is just this guy. Wait, KSP is given and K formation. Both are different thing. So it's this reaction that's happening and K formation for AgNH3. Oh yeah, it's gonna be this guy. So it's from coordination chemistry, I think. So Ag plus 2NH3 gives that the complex, right? That thing is having coordination. That thing has formation constant as Kf. And it's that. Okay, that's weird actually because, huh? So you know what constant of Ag plus into constant of NH3 squared upon concentration of AgNH3 twice is going to be, right? In this reaction, AgCl gives, well, that will happen anyway. That's like a constant that is going to happen anyway. Yeah, and that's also upon divided by. Okay, this is weird. You know, let's write some equations. So concentration of AgNH3 2 plus upon concentration of Ag plus concentration of NH3 squared, that thing is Kf, and concentration of Ag NH3 2 plus upon concentration of, okay, that times concentration of Cl minus upon concentration of 2 NH3, it's like it's going to be NH3 squared. That thing is so you're doing that reaction, but then for AgCl it's just Ag plus and Cl minus. There's, wait, so is this like KSP for this reaction is given, or for AgCl's normal dissociation that just Ag gives Ag plus and Cl minus? Is that thing? I don't know what they want to do. So I'm going to say no. Ag plus and Cl minus. This guy is actually like KSP. And what do they want us to figure out? Minimum moles of NH3 required so that to be added to 1 liter solution so as to dissolve 0.1 mole of AgCl. Oh, KSP is given. So it's gonna give out Ag plus and Cl minus, and that Ag plus will then react with this, right? If this thing is 0.1 and this is like 0.1 minus x. In fact, no, let's just talk about molarities. What solution? 1 liter solution. Well, that's nice, and it's just the same thing as molarity. So 0.1, 0.1 minus x. This thing will be in x amount. NH3 is just what we don't know what it was. Minimum moles. Whatever n that was, n minus x, and this is x, right? So what do you know? You know that x upon x into n minus x. Hey, shouldn't be n minus 2x over here, right? So n minus 2x squared, that thing is kf, and 0.1 minus x times 0.1, that thing is ksp. Ksp is where is it? 10 power negative 10. Oh, that is very small. So it's gonna be 10 power negative 9. Yeah, so the only way for this to actually happen is that if x was very close to 0.1, because look at that, it's so small. So x is approximately 0.1. That's the thing. Okay, then this just becomes 0.1 over here. This just becomes 0.1. This just becomes 0.2. Right, so then 0.1 upon 0.1 into n minus 0.2 squared, that thing is our kf. Kf is given as 10 power 8. This cancels, that means n minus 0.2 is 10 power negative 4. Right, so n is approximately 0.2. There we go. That's the number of moles that must be added. Where is it? Question number 23, right? So it's 0.2 moles. Is it not correct? Mm, whatever reaction. Dissolve one, dissolve 0.1 mole of AgCl. Yeah. Hey, come on. So all of the Ag plus, it just got converted basically. Why is this not doing this? Oh wait, why is this X? Oh come on. Right now Ag plus is just not there actually. It's like 0 point. That's where everything went wrong. So 0.1 over there, and uh this thing is X. That's so this is actually negligible, right? It's like KSP upon 0.1, which was, what was it? KSP was 10 power negative 10, right? So it's like this is 10 power negative 9. So this must have been 10 power negative 9, and this must have been 10 power negative 10. Sorry, 10 power negative 1. And this would then be 10 power 8 over there. Oh, well, that's nice. That means n minus 0.2 squared. That thing is approximately 1. So n is 1 plus 1 plus 1 plus 0.2, which is 1.2. That should be the answer. So it's D. Right, calculation first. Sorry. And last question number 24. Oh no, it's not the last. So there's two. For pure water at 25 degrees Celsius, concentration of H2O is 55.5 mole, 1 gram per centimeter cube, 1 gram per 10 power 3 liter. It's like 1 upon 18 mole per that, right? Hold on, that's the concentration of H2O at 25 degrees Celsius. It's not 10 power negative 15, so B is just wrong. C is alpha is 1.8 10 power negative 9. Well, this concentration times alpha is 10 power negative 7, right? So yeah, it's like 18 into 10 power negative 10, which is the same thing as that. So C is correct. What about A? Is this guy 55.55 mole decimeter? Okay, 9. Let's 0.5 over there. So 5 to 10 power 2, because yeah. So 500 basically, 500 upon 9. Is that like 5 minus 4, 5? Just wait a second. Right, so where was I? Sorry, keep on going away. Question number 24. What was I doing? Yeah, 500 upon 9. That is in fact 5.55 something. So A is also correct. So then A and C both are correct. That means B. Question number 25. When a solution of benzoic acid is started with NaOH, the pH of the solution is 4.2. When half the acid is neutralized, the dissociation constant of the acid is... Oh, okay. That is not part of this sentence. So pH is 4.2 when half of the acid is neutralized. Or we can say seemingly neutralized. That is, you think it is, at least. The solution of benzoic acid, a weak monobasic acid titrated with NaOH, just Ha giving A minus plus H plus, and you have titrating with NaOH. The pH of the solution when half of it is gone away. Okay, so then these two concentrations are the same. That's what they are going for. right? The pH at that point. You don't give the pKa for that? Oh, you gave the pH. That's all you gave. Okay, fine. So like concentration of H plus will be the same thing as Ka. So pKa is the same thing as pH. Right. So it's just 10 power negative 4.2. That is our pK. And what is 10 power negative 4.2? 10 power negative 0.2 times 10 power negative 4 and 10 power negative 0.2. What is that? Oh, that's like multiple. Okay. No, these are close, very close. It's a negative. Oh no. Okay, write it like this: 10 power 0.8 into 10 power negative 5. And oh, so these are 10 power negative 5 over here and 0.8. Hmm. That's like it gets closer and closer to 1. Well, 0.3, 10 power 0.3 is 2. So 0.6 would be 4. 0.8, no, sorry, 0.9 would be 8. So between 4 and 8. That's definitely not 3.2 then. None of these actually. Right, so it's also not this. So it's like A, hopefully. So there it is. So let's check. The next section is not big actually. Okay. Uh, where, where is it? Where is it? IITJ name. Right. So first B, second A. What? Sorry. Okay. Yeah. A. I was going for fifth directly. That's not. Then B. Then wait. What question number 3 is also A. Okay. This is not good. So it's A. Hmm. Okay. Question number 4 is B. 5 is A. Okay. A B B A. Why? 13B. 14B. 15B. 16A. 17B. A. C D E. Okay, 21 was C. Okay, C, then D E A. So let's check what went wrong. Question number 3, question number 5, and question number 12. And that's why did these go wrong? Question number 3. So for this reaction, the equilibrium constant is okay. Question number 3. Wait, what's this? No, that's not what I was doing. No. Zinc salt is mixed with NH4 twice S of polarity, something the order than yeah, this question. I just don't know what the reaction for this is. Oh, okay. No, this we do know. So Z and S, right? So it's like Zn plus S, like precipitating. And they gave A as the correct thing. So okay, while I had C as the correct thing. Huh. Zinc salt is mixed with something of molarity 0. Okay, the amount of zinc the milliliter of the solution would be. Right, so KSP is given, then this thing is just 4.51 into 10 power negative 24. That's the KSP upon the molarity of S2 minus, which is 0.021. Okay, that's the concentration of Zn2 plus and the amount of Zn2 plus in mass basically. So this times the moles and how many moles are there? Sorry, this times the volume, 12 milliliter. So it's gonna be 0.012. Okay, and that times the mass, and we already got that zinc is around 30, so 60, right? This can be written as 21, this will be 1 2, and this can be written as 7 and 4. So 60 into 6, okay, 18.04 10 power negative 24 upon 7. So 6 times that, that's going to be 0.246 of 8, 4 carried on 6, and it's going to be 10. 108.24 into 10 power negative 24 upon 7, which is 1, and then 5, then 3.2, it's like 4, 28. Yeah, 44 something, like 6 maybe, 10 power negative 24. So 1.5 something. Okay, and all of that is good and all, but that's just the mass, right? That's what we were looking for. Of course, that's what we want, right? And question number 3. So yeah, like 10 power negative 22. No, it's not 22 over there. That's the okay. 60 times 18.04. Okay, so 6 times that, it gives this. Oh, where did that 0 go? It should be 23 in that case, and this will be 23, and then this can be written as 1.546 to 10 power negative 22. Okay, so it's close to that, but then it could also been anything like okay, cool. So what I got was wrong, but how was it wrong? Like, what did I do? I don't remember it. Oh, okay. So I think I might have divided this number by 60 instead of multiplying. That's why it went wrong. So okay, third is wrong. Fifth, what is the percentage hydrolysis of NaCN in, okay, when dissociation constant for HCN is this thing, in Kw is this thing. So fifth, they gave A as wrong, and they gave, sorry, they gave A as correct and C as wrong. C is 8.2. So Kw is like 10 power negative 14 upon that, so it's going to be 10 power negative 5. Right, this is our forward reaction constant, and sorry, forward reaction equilibrium constant, and this will be concentration of, what do you want? You want the, what do you want? Percentage hydrolysis in normal upon 80 solution, right? N by 80, whatever. So C into alpha squared upon 1 is alpha, of course. What else would it equal be? And that's what we're looking for. And C is just 1 upon 80, right? So this will be 8 into 10 power negative 4 upon 1.3 is equal to alpha squared upon 1 minus alpha. So we will be assuming that, okay, alpha is small, then cancel this away, and then alpha is 10 power negative 2 times square root of 8 upon 1.3, I think. Yeah. So is that small? Yeah, I think like 0.02, that times what's this, like 8 upon 1.3. So for 80 you would have 78, which is 6, so 0.6, right? That would be 0.6 over there. So square root of that, okay, not the most nice things, like 0.64 if we want. So 0.8 maybe, 0.8 into 10 power negative 2, that's going to be 0.8. Wait, what? That's not into dissociation, right? What do you want in terms of percentage? Wait, what? Something's going wrong. percentage hydrolysis, right? Uh, something's going wrong. 0.85 upon 1.3, that thing is equal to alpha upon 1 stuff. So 80 to 10.84 upon that. Okay, so square root of 8 upon 1.3. 8 upon 1.3 is approximately 0.6 because, yeah, like 6 times that, it's going to be 6, 18, 78, 0.78, very close to, no, actually not square root of 0.6, but 6 itself. Yeah, yeah, so it's only square root of 6. Okay, square root of 6 is like close to 6.25, which is 2.5. Yes, like the square of 2.5. So 2.5 to 10 power negative 2, that still gives. Oh, so yeah, this thing A is very close to 2.5. Fifth, A is good. What was I doing incorrectly then? I don't know. Okay, so that's wrong. And question number 12. What's question number 12? So they gave the D is wrong. Then what was correct? Right. Yeah, this thing. I didn't understand what this question was. So I'll just leave it like that. Okay, so I'll see you guys in the next video.